Good afternoon, everyone. And Adrian, thank you. What a wonderful event. What a wonderful turnout. It's great to see the interest as it relates to hydrogen. So, I'm going to talk about a particular case study that we're working on with a mining company which has asked to remain anonymous for now. They want to do their own due diligence around integrating hydrogen into their particular new mining operation. But I can at least talk around some of the figures and what we've seen through the techno-economic assessment that we've done on this particular mine. So first of all, to start off, why is hydrogen becoming an interest? I mean, we've talked about hydrogen for decades now, and it's never really got off the ground. And these are some of the key drivers. One is the cost of renewables. The cost coming down over the last 10, 15 years, considerable costs coming down, and the increased uptake in renewables as a result. And with this increased uptake and the variability of renewables, we need something that's not only going to stabilize our system through a demand-side managed load. These are these large utility-grade electrolyzers, but also hydrogen storage becomes a very important component. We saw from the CSIRO curve earlier on that remote area power systems are likely to be the first cab off the rank, the low-hanging fruit as far as hydrogen projects, and we're now starting to see this happening in potential greenfield new mining operations that are about to take off, that are in very remote areas and existing remote towns that rely on diesel or compressed natural gas. So policy and the cost of renewables coming down is definitely a driver that's changing the way we see our energy in the future. So let's look at what we now do as far as our mining is concerned. We can either look at connecting our mining operations to the grid through an overhead line, or do self-generation on site and pipe that diesel and or gas to site and generate power on the site that way. However, when the mine is very remote from either an electrical grid or a piped gas network grid, then we need to look at a virtual pipeline. This is bringing in diesel or gas or LNG using a truck, and remoteness of that brings the cost of that fuel to site up, and so now we need to look at where it makes sense to start making our own fuel on the particular mining site to serve our operations. So what we're seeing today is, and we've seen this with Goldfields, De Grissa, the Sandfire project. We've seen it with the Opal Mining, Cooper Pedy, where they're now starting to integrate renewables into their mining operations. So this is solar, preferably wind, battery storage, and the traditional type of generation that they would use, be it diesel or gas generation. And what they're doing is they're now starting to offset their requirements for fuel on their particular plant with those renewables. And it only makes sense where the fuel to get, the cost of getting that fuel to site is very high. So we look at what the levelized cost of energy is, and we assess what makes sense from both a technical point of view and an economical point of view. Now, if you look at our particular project that we looked at had a peak load of 35 megawatts. The capex spend for a diesel or gas plant would be approximately $25 to $43 million as an upfront capex to get that power plant going. It would rely on diesel and or gas to be brought in by a truck. And that over a 20-year period, the 20-year mine life would account to about $1.2 to $1.4 billion worth of fuel costs. And this is what we want to try and offset, is that operational cost associated with the fuel. By integrating renewables, if we've got a complementary wind and solar resource on that site, we can offset the amount of fuel that we rely on by about 70%. So that means we can reduce our fuel operational costs by about 70%. This could be the difference between a mineral resource that's sitting in absolutely middle of nowhere being available to mine or not. We know that Australia is vast in its size, and we've got mineral resources that sit in the middle of nowhere. And most of those resources haven't been accessible to us because the cost of energy to build an overhead line at approximately $1 million a kilometre, or a pipeline at about $1 million a kilometre. So now what we're doing is we're opening up the opportunity to mine those resources that are very remote, with the energy cost still consisting of about 50% of the total mine operational cost going forward. But there are further considerations to take into account, and this is where hydrogen comes into play. So where we have complementary wind and solar, and we're tracking to that 70% renewable content, there will be times where there is more power generation coming from, and in most cases the wind, than we can utilize in the plant. In fact, it will destabilize the power system if we don't absorb that energy or curtail it. And what we found on this particular site, about 50% of that wind and solar would need to be spilled through the period year on year. So it's that 15% of spilled energy over a 20-year period per annum. We take the value of that and we say, okay, well, let's put that aside, that capital cost that we're going to, or that energy that we're going to waste, the value of it, let's assign that to the spend on CapEx to put the electrolyzer technology in, and start to increase the amount of renewable content in our plant and see where it makes sense as far as the utilization of that hydrogen. And there are a number of possible value streams that can be seen there. We can re-electrify on site. So what we're trying to do is offset diesel in this particular instance, which costs approximately $1.08 per litre. 78 cents per litre is the base cost, and then an extra 30 cents to deliver that diesel to site, which is probably about 800 kilometers away from the nearest port where the diesel comes in. The other area that we could use that hydrogen is, and we've talked about this in length today, is as a transport fuel. And in particular, the interest around that hydrogen going into the prime movers. So this is the ore body being moved from site down to port. That being anything from 800 to 1,000 kilometers away. You've got your excise tax on the fuel. This is where you're going to get your best bang for buck for that hydrogen. And we know that Nikola is a company in the US that's looking to build these road trains, these fuel cell road trains, and we could expect to probably see those things on the road within the next year or two. Other areas where hydrogen could be used is the production of ammonia on site for ammonia leaching. I think in most cases we rely on sulfuric acid leaching, if I'm not mistaken, but there are also, ammonia has also been part of the leaching process and is something that could be considered. So it's looking for these multiple value streams associated with hydrogen that then makes it stack up. And this is what's very important in getting the cost right. So you may ask where Siemens play as far as this technology is concerned. Well, we start with our partners, our customers, in developing a techno-economic assessment on their particular vision, and we go all the way through to delivering a complete solution, turnkey, and bring finance into these projects. Siemens is an electrical engineering company, OEM. We provide all the electrical technology, including the electrolyzers, battery storage, solar PV technology, but we bring the whole solution together and we provide the ongoing services and support to ensure that that plant meets its KPIs running forward. So this is where we start. We have a tool called PSSDE, and this is where we start to model our power plant and do the techno-economic assessment to work out. Not only will it work technically, but it will bring about the commercial targets required by our customer or partners. So for this particular case study, there's a lot to read there, but I'm going to point to the main important points. So project commencing approximately around 2023. Solar, 2.188 kilowatt hours per day at a 35% degradation each year. We've considered a 7.42 meter per second wind profile. We got about 5 months worth of actual wind data from their MetMast. And ideally we want a year, but it's at least giving us a bit of an insight as to what wind profile, what wind resource we have in this particular area. The target return on equity is at 14% with a WACC of 7.13. We've considered a gearing of 30-70, project term of 20 years, debt repayment of 15 years, escalation on fuel at about 2.5% per annum, so this is diesel, and an escalation on the O&M costs of 2.5%. The energy fuel price I mentioned earlier, 78 cents a litre as the basic cost, plus 30 cents to transport it to the remote site. We've also taken into account ACCUs. This is Australian Carbon Credit Units. This is voiding carbon emissions. For every tonne that we avoid as emitted, we get about approximately, we expect by then, around $15 a tonne. And then I'd just like to point out that we should note that displacing diesel fuel for transport on our roads would be at about $1.50 a litre. So that's important to consider. So we modeled approximately over 50 possible scenarios, and what I've done here is I've brought up 4 particular scenarios with the reference being reference 0, where it was only a diesel plant. And why we consider diesel rather than gas, the mining operations are going to be very reliant on diesel as a fuel for its trucks for the mining process. So rather than managing 2 possible fuels to site, we consider diesel as the logistics around 1 fuel would be a benefit over trying to manage multiple fuels. Scenario 1 looks at wind with battery storage and the traditional generation of diesel. Scenario 3 looks at wind and solar. Scenario 4 looks at only solar. And scenario 45 is the one where we include the hydrogen. And in that particular instance, we've looked at an 8.75 megawatt electrolyzer, PEM electrolyzer, and 1.5 megawatts of fuel cells to re-electrify and offset some of that diesel. So over here we can see, and it's the smiling faces and sad faces that I'd like to point you to. The capex of the diesel plant is very attractive, very low, but you'll see that the levelized cost of energy is very high at 38 cents a kilowatt hour, or $38 a megawatt hour. If you look at scenario 45, the capex is very high, and I put a sad face there for the miners, but the banks and the financiers are probably smiling at that one, thinking, well, here's an opportunity to put our stored cash somewhere and earn equity. So that could potentially be a smiley face. But you can see the levelized cost of energy is 22.6 cents a kilowatt hour. Now that's not too different from scenario 3, where we have solar and wind. It's slightly better at 22 cents a kilowatt hour. So the solar wind only beats it. But we can adjust the size of our hydrogen technology to meet the same price and at least have something there. But as the costs of the electrolyzers and the fuel cells come down, we can expect that we can start to beat that 22 cents a kilowatt hour. But what's also compelling there is our renewable energy percentage content. So with the hybrid power plant solution with hydrogen, we have a 71.38% renewable content on that particular plant versus scenario 3 at 67.78, so slightly better. But the hydrogen technology that we would put in is both modular and scalable, so as the cost of this equipment comes down and as the price uncertainty around fossil fuels makes it harder for us to use a diesel or gas, we can get more certainty around the hydrogen application, and we can start to increase the amount of hydrogen in the plant as it improves. This over here gives you a bit of an idea of the amount of hydrogen produced in a year. So that's just over, so that's 577.5 tons of hydrogen would be produced by that 8.75 megawatt electrolyzer. The energy from the wind is 28.85 gigawatts of energy. That would have normally been curtailed, which we're now directing into the electrolyzers. And the electrolyzers are at the same time providing a service to help balance that energy system with that demand side managed load. Water, very important. In the middle of nowhere, we don't necessarily have water available at our discretion. And so with the use with the fuel cells, we try to keep that water within a closed loop. And through that, we would only lose around 20 to 25% of the water. So what comes out of the fuel cell is pure water, which can go directly back into the electrolyzer. Potable water, we're looking at about 16 liters per kilogram of hydrogen produced, and demineralized, deionized water, about 9 to 10 liters. So out of the fuel cell is that demineralized, deionized water. So we turn that back into the electrolyzer and not have to purify the water with that parasitic load that is required to purify the water. But noting that water is almost an irrelevant cost when it comes to this technology. It's really the cost of energy that is most important. This over here is the fuel cell. So we're working with Hydrogenics and looking at their fuel cell technology. There are other suppliers in the market like PowerCell, and we've heard from Ballard today. We're looking at a 1.5 megawatt unit which can scale up. It will use almost all that hydrogen that would be produced by the electrolyzer. There would be excess hydrogen of about 25 tons per year. And that could be redirected to other things like mining vehicles. So, having a look at the actual output from our modeling tool, this gives you a bit of an idea of the load profile. It's a synthetic load profile that we produced from actual load profiles on other mining operations in the area. And what we did was we adjusted it to suit this particular mining operation. You can also see it over a 7-day period. These three graphs, the top graph shows all the wind, solar, electrolyzer switching on and off, diesel engine switching on and off. Just too much to see there, but it's the bottom graph that I want to point you to, because that over there gives you an indication of the total curtailed energy on this particular case study, on this particular mine. This is the amount of energy that would be curtailed, and the red area is the amount of energy that we would direct to the electrolyzers. So essentially the amount of energy we would absorb with the electrolyzer and turn into hydrogen. Now we could absorb all of it, but it doesn't make sense from a cost point of view. So that was the optimal cost point of view in this particular case. So a little bit about the technology itself. This is our third platform, the Siemens 300. It has 24 modules. Each of those little blocks is a cell of around 730 kilowatts each. That unit, at its nominal rating, will produce about 340 kilograms of hydrogen an hour. It's 75% efficient in total. The actual electrolyzer blocks, the PEM electrolysis blocks, are around 81 to 83% efficient on their own. The water is pushed against the proton exchange membrane using gravity, so we don't use pumps and motors because we want to get those parasitic losses as low as possible, and the hydrogen comes out at atmospheric pressure. This gives you a bit of a detail on a bit of a spec sheet on the actual electrolyzer itself. You can see that the purity is around 99.9%. It comes out slightly wet, and if the fuel cells, we know that in vehicles, they like it 99.99995% pure, so the hydrogen would need to be dried out. Plant availability is very high, and depending on where this technology would be applied, a total solution would cost in the region of about $1.5 million per megawatt. This over here indicates the scalability. So I mentioned on this particular case study, we were looking at an 8.75 megawatt electrolyzer, so that's half that size. It can scale up to 17.5 megawatts by just inserting more of the little cell blocks of 730 kilowatts each. But then the 17.5 megawatt blocks can be scaled up to hundreds of megawatts as required by the particular plant. And this will give you a bit of an idea of the size and footprint of a 70 megawatt system with the cooling on the side of the building versus the cooling on top. As you can see, the footprint is very small. And when you're looking at about 35 megawatt hours of stored energy as hydrogen, that can be done in a single 40-foot container cube. So if you look at that compared to, for instance, the Tesla battery down in Australia, 4 40-foot cubes, one on top of each other, and you've got the equivalent stored energy as that large battery in South Australia. So very small footprint, but that at 500 bar. This over here was the largest PEM electrolysis hydrogen production plant put into service in middle of 2015. Its nominal rating at 3.75 megawatts, but its high output rating at 6 megawatts for 15 minutes. So it's 3 of our Siemens 200 platform units, and that hydrogen is being served not only into the gas grid in mines just outside Frankfurt, it also goes to a glass factory for production of flat glass, and it also goes to fueling stations in the region for vehicles. So this is where it's important, where you have those multiple value streams, hydrogen starts to play a role. There are a number of other projects that we're delivering. One was for a steel plant. This is to decarbonize their steel process and move away from coking. Also in Germany, and the other one that we're about to, I think we're in the middle of commissioning, is a 6 megawatt plant in Austria. Sorry, that one's for the steel plant. The other one was for the H&R GmbH, is for a cosmetic company that's making cosmetic oils from renewable sources rather than carbon-based sources. We're in the process of delivering the largest PEM electrolyzer in the country, which is a 1.25 megawatt unit. It's a tiny little one, as far as we're concerned. It'll produce about 22 kilograms of hydrogen an hour. We're doing this with AGIG. It goes into a microgrid in South Australia called Tonsley Park, and we're expecting commissioning to begin towards the end of this year, first quarter next year. We're now looking for the double-digit projects, and it's the RAPS, Remote Area Power Systems, where we believe we'll see the low-hanging fruit going forward. And that is all from my side. I hope that was interesting.
Thank you.